So last unit we were doing confidence intervals. What was the goal of a confidence interval? Why did we make those confidence intervals? Okay, good. We wanted to kind of balance our risk of being incorrect. Good. And what were those confidence intervals doing? Like, what were those numbers even about that we were estimating? When we would say that we're 95% confident of this interval being right, what was that interval about?
Populations versus sample.
A population value. So what we were doing with confidence intervals was we were estimating possible values for the true parameter. Okay, so we were estimating possible values for the true parameter. So for confidence intervals, we were estimating parameter values that were possible. So based on our sample, we would give kind of a range of data or values that could be possibly be the truth. So where the shift is that with a hypothesis test, we're not really going to have a range of values anymore. We're going to have a single value that we're going to basically put on trial. Okay, so we're going to have some claim or something that has been true forever, and we're going to try to prove it wrong. If we can prove it wrong, then obviously we have done our job and we have shown that the claim is incorrect. If we can't get enough evidence to prove it wrong, then we're just kind of stuck with what the claim is. Okay, so we're like statisticians that put numbers on trial. Okay. When there's an actual trial, the person is always what? Until proven guilty.
Innocent.
Right. They're innocent until proven guilty. So whatever claim is given to us or whatever has always been true in the past is going to be the truth unless we can prove otherwise. If we can prove otherwise, fine. If we can't, then we're just going to have to stick with what the claim is. Okay. So these are called significance tests. Significance test. They're also called hypothesis tests. They're kind of interchangeable words there. So these significance tests, what the goal is. So the goal is to evaluate a particular claimed value. We're going to evaluate a particular claimed value. So we're going to be told that the value of the parameter should be this, and we're going to evaluate that based on the evidence that we are given. Okay? Cool? Cool. All right, so here's an example. Our buddy, Coach Brooks next door, he says he's an 80% free throw shooter. But you look at the guy and you go, yeah, right. No offense, Coach Brooks. Maybe a little. So what we're going to do is we're going to let him do a trial of 25 shots. Since he's busy teaching right now, we'll do it virtually. So we're going to go to right here. So here is his claim. Coach Brooks claims to be an 80% free throw shooter. We're going to give him 25 shots to prove his worth, I guess, if you will. So as this, you'll see the basketball shoot here. If he misses, he's going to miss to the left. I don't know why, but it is what it is. But it'll also calculate the percentage of hits and misses. You'll also see a line that will keep moving as he goes on whether or not he's hitting or missing. So here we go. Good luck, Coach Brooks. Oh boy, this is not looking good. It's looking like Coach Brooks is not as good as he claims to be. Are we shocked?
No.
Oh, all right. So it looks like he only hit 44%, and he says he's an 80% free throw shooter, y'all. So based on this evidence, do we believe his claim? No. And we actually have some pretty good evidence to prove that he's wrong And it was his own evidence. He gave us this evidence. So, like, it's kind of looking like he's maybe a little bit of a liar. So we would probably say, yeah, whatever, Coach Brooks, you're not an 80% free throw shooter. You're a bum. We all knew that. But he goes, wait a second, y'all. That's not fair. I wasn't even warmed up yet. I came in cold. You didn't even let me warm up. So let me warm. Okay, now I'm warm. I've done some shots here. Now let me try again. So we're going to say, okay, you know what? It could have been a bad sample. Maybe we didn't allow you the warm up that you deserved. So we're going to allow you to do it one more time. But this is it. All the marbles right here. Go. All right, he had a little bit of a run there at the end, but do we believe that he's an 80% free throw shooter based on this data?
No.
Yeah, not so much. Still pretty low based on where he should have been. So we would say we have good evidence to say that the claim is incorrect. That's kind of how this works. We get our evidence from taking samples, like taking this sample right here. So that's where we get our evidence from, okay? So if I go back to this, dun, da, da, da. The first time, what was he, 40-something?
It was 11 shots made.
11 out of 25, so that's what, that was like, what, 44% or something? It doesn't really matter. But anyways, and then he was, that second time, he was like 50, 48, 50? 56%? Okay, cool. All right, so are you convinced that Coach Brooks' claim is true, or do you think that he makes less than 80% on average? Less than based on the evidence. We are statisticians that like to have evidence. We need evidence to back up our what we find and what we say. And so it does appear that based on our evidence that Coach Brooks is not as good as he claims to be. So sad. So that's kind of how these work. Somebody or something makes a claim, or we have something that's been true forever, and then we try to get evidence to prove otherwise, usually through taking a random sample. And then whether or not our sample matches what it should, then we can say whether or not it's a true statement. Now, there is one little problem, right? Because that seems pretty straightforward and pretty easy. But here's the thing. There are actually two explanations for why we get a different statistic, a different sample than what we should get, which is the parameter value. So the first reason is what we kind of concluded with Coach Brooks. The claim is incorrect. This is the innocent person is actually found guilty because guess what? They were not innocent in the first place. Okay? So the claim is incorrect. That's wrong. Coach Brooks is not an 80% free throw shooter because he's just not that good. So there you go. That's one reason why our statistics, our sample, does not match the parameter or the claim value. But what's the other reason that could be why our statistic, our sample, doesn't match the parameter? Why might that happen? If the claim is truly correct, why does our sample not match the claim?
Bias?
Could be there was some bias in our sample. That could be. What else? There's one other thing that could be true. Say that again. Possibly I didn't allow for enough trials. Okay, so that might kind of go with bias, but yes, very good. So the sample is not a good representation. And this could be due to bias. So that would be kind of our fault. If we took a biased sample, that's kind of like tampering with evidence in a trial. You don't want to do that. That's really bad. The sample's not a good representation due to bias or basic old sampling variability. So Did you know that there are some people who go to trial that are innocent and they are actually found guilty? Why does that happen? So it could be that they had a biased prosecutor that made up evidence. It could be that. Or it could be that the sampling variability. There's kind of this window of, did you do it or did you not do it? It's kind of unclear. And then the jury has to decide, was that just kind of a little bit of a coincidence that that person was there at that time? Or did they actually commit the crime, or what's going on? There's a little bit of sampling variability that can happen with our samples. And sometimes we look at that and we go, you know what? That's too far away for me to believe that it was just sampling variability. But sometimes we look at it and go, you know what? That was probably sampling variability. And sometimes guilty people get to walk free because the sampling variability is there, right? There's some variability in the evidence that's kind of like iffy. Don't really know whether or not that's true. I was on a jury, not this past jury duty, but the one long time ago. I was on a jury where it was a drunk driving case. The guy was 100% driving drunk. I have no doubt in my mind. But the evidence that was presented, which is the only thing you're allowed to go on, the evidence that was presented and the way that it was presented, there was some variability in the story that made it where, okay, I don't think that we can really say for sure that he was driving drunk because of this one little variable that's in his story. But every one of the jurors said, we think that he was driving drunk, but because of the variability in the evidence, we can't find him guilty. So that man who was driving drunk got to walk out as an innocent man because of the variability in the evidence. That happens in stats as well. So there's that. Okay. So what we have here is we have hypotheses. You guys all took middle school science, yes? Yeah. What's a hypothesis? Sort of. It's a question that you have, and then it's a...
I was like, you're making like a prediction about something happening.
Absolutely. You're making a prediction about something, and where do you get that prediction from? Is it just you just kind of shot in the dark, or you just kind of draw a number out of a hat, or draw something out of a hat, or how do you make that prediction?
Given information.
You're given some information, and you make an educated guess, right? Do you guys remember educated guesses? Yeah. All right. So that's basically what we're going to do as well. We're going to have two different hypotheses. We're going to have the null hypothesis. Now, the notation for the null hypothesis is a capital H with a little 0 in the subscript. That's the null hypothesis. Capital H with a little 0 in the subscript. This is sometimes lovingly referred to as the hoe. You'll see why that will help us later. So, the null hypothesis is basically this is the claimed value. This is kind of this is the innocent, right? You're innocent unless we can prove this other thing that I'm going to tell you about in just a second. So, this is the claimed value for the parameter. Again, all of the things that we're doing are in regards to the parameter value, the population value. And so the null hypothesis is the claimed value for the parameter. Now, we are very skeptical statisticians. We don't believe anything that we see on the first try. So we're going to try to prove that wrong every time. And we come up with something called the alternative hypothesis. That is a capital H with a little a in the subscript because we're laughing at that null hypothesis. We're going, that's not right. This is what it should be. All right. So we've got our null hypothesis. That's the claimed value or what has always been true. We're going to give our alternative. And this is going to be based on the suspicion or the thought or the hope that we are thinking is going to be true. Okay, so this is our suspicion or hope about the claim. So it's always going to be in terms of the claimed value. I'll show you what I mean in just a second. But basically, if Coach Brooks comes in here and says, I'm an 80% free throw shooter, we're not going to look at him and go, no, you're not. You're a 50% free throw shooter. We're going to have an alternative that is in terms of his claim. So if he says he's 80%, we're going to go, no, you're not that good. You're less than 80%. We might look at him and go, yeah, oh, you're being humble. You're better than that. So maybe greater than 80%. Uh-oh. Or it might be that we look at him and we go, you know what? You're not an 80% free throw shooter. We don't know if you're better than that or worse than that. We just don't think it's 80, which that would be kind of weird for that particular situation. But that can be your alternative as well. All right, so let's look at how to format these things. In any significance test, your null hypothesis is going to have the same format, okay? So your null hypothesis. You have your null hypothesis notation, capital H, a little o, and you're going to have your parameter. Now, when I say parameter, you guys know I mean Greek letters, right? Mu, P, sigma, those are your parameters. It's going to be one of those, right? It depends on what the problem's about. Is it about means? Is it about proportions? Standard, like what is it about? Your null hypothesis is always going to have an equal sign every time. Every single time your null hypothesis is going to have an equal to sign. And it is going to equal the claimed value. It will equal the claimed value, whatever that claimed value may be. The alternative hypothesis is going to have one of these three different ways. Either you think the parameter is greater than the claimed value, less than the claimed value, or not equal to the claimed value. The value that you're using here is the claimed value from the null hypothesis. It's the claimed value from the null hypothesis. Again, we cannot give an alternative number. We just have to say what it is in terms of the number that was given. Less than, greater than, or not equal to. Now, how do I know which one of these do I use? It depends on your suspicion. Okay? It depends on your suspicion or hope. You'll see this will make more sense when we do our examples here at the end. All right, so before we do our examples, I do want to give you guys a couple of hypothesis stating cautions. These are going to be things I want you guys to be very careful about when you're writing your hypothesis statements. Okay? So the first one is the null hypothesis always has an equal to sign. You will never say that the claim is that the number of red cars is bigger than 100. Like, that's not a claim. Like, the claim is a certain one number. It equals a certain one number. Okay? Your hypotheses are only about parameters, not statistics. What I'm saying here is that you will never see an X bar, a P hat, or an S sub X in a hypothesis statement. If you do, it is wrong, and you should never use it. Your hypotheses are always about the population. Just like your confidence intervals were always about the population value, never about the sample. Now, are we going to use sample data? Absolutely. The sample data is where our evidence is going to come from. But the hypotheses are always about the parameter. Cool? Cool. Let's do a couple of examples. Pineapples. Any of you guys been to Hawaii and eaten pineapple there? Yeah? When you come back, it just doesn't taste the same, does it? It ruins your pineapple eating experience. It really does. Huh?
Pineapple eats you back when you eat it because of its acidity.
It does. That is a true statement as well, yes. But when you eat pineapple in Hawaii, it's very unacidic. I don't know, it's just different. Anyways, at the Hawaii Pineapple Company, managers are interested in the size of the pineapples grown in the company's fields. Last year, the mean weight of the pineapples harvested from one large field was 31 ounces. A different irrigation system was installed in this field after the growing season. Managers wonder if this change will affect the mean weight of pineapples grown in the field this year. State the appropriate hypotheses for performing a significance test, and be sure to define the parameter of interest. I'm going to show you guys how to do that. It's not that hard, but it does start some sentence writing. You guys love sentences. Yeah. Null hypothesis, alternative hypothesis. When you guys are writing hypotheses, you're going to need both, okay? Then you need to decide, what is this problem about? Is this about means, proportions, standard deviation, something else? What is this about? This is about a mean. So my parameter, when I'm talking about means, is mu. So we've got a mu. Now, the null hypothesis is that the mean is going to be what the mean has always been unless we do something different, which we're trying to do. But what was the mean of this field last year? Yeah, so the mean equals 31 ounces as shown last year. But this year, we have a new irrigation system. And we are wanting to know if this will change and affect the mean. Does it say that we hope that the irrigation system gives us bigger pineapples?
No.
Does it say that we're worried it's going to give us smaller pineapples?
No.
It just says we're wondering if it's going to change the pineapples. So our alternative is we're wondering if the mean is different, not equal to 31 ounces. Okay, define our parameter. The parameter we're using here is mu. So basically, I just have to write a little statement about what is mu in this particular problem. Mu in this particular problem is the true mean weight of pineapples in this field. That's the mean. That's not so bad, huh? And that would be all you would have to do in a problem like this. We're not to the math yet. Trust me, we're not going to get to the math for a while, but that's how you would write these hypothesis statements. Cool? Cool. All right, next, let's look at this problem. Are you college bound? The U.S. Bureau of Labor Statistics estimates that 69.7% of high school graduates enroll in a college or university. Bernard has great pride in the quality of his large school. He thinks the proportion of college-bound students is greater for last year's graduating class. State the appropriate hypotheses for performing a significance test, and be sure to define your parameter of interest. Again, we're going to have a null and an alternative hypothesis. Now, what is this problem about? Mean, proportion, standard deviation.
Proportion.
This is about proportion, so we should use P. Not P hat, because that would be about the sample. We're not talking about the sample here. We're talking about the population. All right. The null hypothesis is that P equals what it has been stated to equal in the past, which would be 0.697 or 69.7%. Yes. So P is 0.697. Now, Bernard, he has a hope, a suspicion even, that at his large high school, he thinks the proportion of college-bound students is greater than last year's claimed value. So what would our alternative hypothesis be? P is greater than 0.697. Okay? Again, we are stating it in terms of the number for the claim, but we are thinking that P is greater than 0.697. And then we're going to define our parameter. P is the true proportion of college-bound students at Bernard's school.